All right, welcome everybody. Only announcements for today is another reminder about the Achieve homework, which is due Monday at 9. And then our first assessment is a week from today. So next Friday, it is going to cover chapters 11 and 12. So we're continuing with 12 today, and we'll continue next week as well. There will be about 14 multiple choice and 3 short answer questions. Okay, so we ended class with this learning check. Which of the following substances can form hydrogen bonds or hydrogen bonding interactions to other identical molecules? So you already did the Eichlicker. So we need to look, let's remind ourselves about the 4 different types of hydrogen bonds. I'll get there. The 4 different types of intermolecular forces. Well, specifically, hydrogen bonding interactions are when there is a hydrogen bonded to a nitrogen, oxygen, or fluorine, and 2 molecules with that condition met interact with each other, and they have a strong force of attraction because there's a strong partial positive on the hydrogen and partial negative on that other atom, the nitrogen, oxygen, or fluorine. We have just polar molecules. They have dipole-dipole. Nonpolar molecules is dispersion forces. And then ion dipoles, we need to have a formally charged ion for that molecular force. I think we skipped over these slides pretty quickly, but this is just another example where you have H2O interacting with another H2O molecule. So we have hydrogen bonding interactions between water molecules. And hydrogen bonding interactions are how base pairs on DNA are connected to each other. So you can see in really small text, there's hydrogen bonding. Those dashed lines are showing hydrogen bonding interactions between those base pairs, so it keeps the 2 ends of DNA connected. Here's some more examples of hydrogen bonding. So it can occur between 2 different molecules. Here's water. We have both conditions met: hydrogen bonded to oxygen, and we have another oxygen. So there's a hydrogen bond between these 2. Here's another one between 2 different molecules. We have water. Water-oxygen is hydrogen bonding interaction with the hydrogen on ammonia, and hydrogen on water with the nitrogen on ammonia. It can happen within a molecule. Salicylic acid is here, and geometry allows for the hydrogen bonded to oxygen to have a hydrogen bond with the other oxygen, and that's a stabilizing interaction within the molecule. Okay, so this first molecule, we have 3 hydrogens bonded to a carbon. Those can't hydrogen bond. But over here, we meet the conditions of hydrogen bonding, nitrogen bonded to hydrogen. So this means another molecule of the same structure can have a hydrogen bonding interaction between the nitrogen and hydrogen of different molecules. So this one does have hydrogen bonding. Again, in B, we have hydrogens bonded to carbon, which cannot participate in hydrogen bonding, but we also have this OH part of the molecule that can. So B, hydrogen bonding. CH4 is nonpolar. So not C. CH4 can only have dispersion forces. And then HCl is polar, but the hydrogen is not bonded to an oxygen, fluorine, or nitrogen, so we do not have hydrogen bonding interactions there. So dispersion forces for CH4 and dipole-dipole as the strongest forces for HCl. Questions on any of these? Okay, let's talk a little bit more about dispersion forces. So the image at the top, labeled as an isolated atom, just shows an atom with a nucleus in the center and then electrons in an orbital, or we can also call that an electron cloud, so a space where electrons exist. On its own, the electrons are evenly distributed, but electrons can redistribute. They're not localized to a specific spot. They can shift around, float left and right, up and down, forward, backward in a molecule. And that distortion or that redistribution creates an instantaneous dipole. So this instantaneous dipole, a dipole results from electron density gathering at one side of the molecule. So if we look at this one, notice how the electron density is off to the left. That means there's a higher concentration of electrons over here, which induces a partial negative charge. As a result, we have a partial positive charge on the opposite side. So if we have a liquid sample of a nonpolar molecule that has electrons redistributing to form a partial negative and a partial positive for an instant and instantaneous dipole, well then a nearby molecule will also have a dipole. The partial positive charge on that original molecule that had the dipole first, well that's now going to attract electrons from a nearby molecule. So the electrons in the electron cloud from a molecule nearby will then move towards the partial positive end. So we have partial positive here, electrons are negative. And then now on this molecule, we have higher electron density on one side, with partial negative, and less electron density on the other, so partial positive. Now this all happens for a moment, but it is still a property that is observed in nonpolar molecules. So reading our bullet points here, first, electrons in a nonpolar molecule can redistribute, creating an instantaneous dipole. And this induces a similar change in charge distribution in an adjacent molecule, and this is referred to as an induced dipole. So the instantaneous dipole to induced dipole interaction may only last for an instant, so it's not necessarily a constant force of attraction between these molecules because the electrons can then move around again. And because of that, this is generally the weakest intermolecular force compared to the other intermolecular forces. So although this is a weak intermolecular force, there are features of certain nonpolar molecules that can make dispersion forces stronger for certain molecules compared to others. So we'll talk about three different features. The first two are related to polarizability. I'll talk about what that means. But this first column is focused on atomic size. So if we have a larger atom, the two examples here of molecules are difluorine and diiodine. Iodine is a few rows below fluorine, so it's a much larger atom. That means there's more electrons in that electron cloud. So if the electrons are shifting to one side, there's going to be a stronger partial negative just because there's more electrons there. So that means larger atoms are more polarizable because there's more electrons that can create a dipole or a polarity feature of the molecule. As opposed to fluorine, there's fewer electrons, there's not as much space for them to move around. So any dipole would be a weaker dipole than for diiodine. We can summarize that here. Larger atoms are more polarizable which results in stronger dispersion forces. Very similarly, in the second column, we have two molecules. The first one has 10 carbons and 22 hydrogens. The second one has 5 carbons and 12 hydrogens. So we have more carbons and hydrogens in this first molecule. That means we have more electrons. Each carbon brings its own set of electrons. So if we have double the amount of carbons, then we have double the amount of electrons from carbon atoms. So if there's more electrons present, then same idea as atomic size, more electrons can be shifted around, and that dipole, instantaneous dipole, can be stronger. The result of this is boiling point. So remember, if we have stronger intermolecular forces, that's in the liquid state, to boil something, you have to break those intermolecular forces. Because when you boil something, it becomes a gas. Two molecules are now far apart. They don't have intermolecular forces between them. So if you have strong intermolecular forces between liquid molecules, it requires more energy to break those and have something boil. Decane, larger molecule, more atoms, has a boiling point of 447 Kelvin. Pentane is 309 Kelvin. So fewer electrons, weaker dispersion forces, lower boiling point, requires less energy to break those intermolecular forces. Okay, so more electrons, well, let's say more atoms, means we have more electrons to be polarized. That results in stronger dispersion forces. And the last feature here is related to the shape of the molecule. So we're looking at pentane, which I'll draw at the top here. It's 5 carbons in a row. It's represented with that ball and stick model, but just to visualize the Lewis structure, I'm not going to draw in the hydrogens, but you can see we've got 5 carbons in a line. This molecule down here, 2,2-dimethylpropane, also has 5 carbons, but they're bonded. We have 4 carbons bonded to a central carbon. And then each of those bonded to the central carbon is a CH3 group. And notice that the boiling point of pentane, 36 Celsius, so we've changed units here, 36 Celsius of pentane, compared to 10 Celsius for the other molecule, 2,2-dimethylpropane. So 10 degrees Celsius, that's lower than 36. That means this molecule with the central carbon bonded to 4 others must have weaker intermolecular forces. The reason it has weaker intermolecular forces is because of that branched nature of the molecule, as opposed to pentane, which is a line. Like if we think about carbons in a row, the next pentane molecule can like sandwich right on top of it. So those molecules can be really snug and close together, as opposed to a branched molecule, they can't get as close to each other. So again, that dipole and instantaneous dipole or induced dipole would be weaker, and the intermolecular force would be weaker. So if we have a more linear molecule, that would also result in stronger dispersion forces. Okay, I think we've got a learning check next. Yes. So it's not gonna be an iClicker. I said we won't do iClickers today. But for these 4 molecules here, your goal is to state not which IMFs, but state the strongest IMF present between molecules of the following pure substances. So remember, dispersion is the weakest, dipole-dipole is slightly stronger, hydrogen bonding is stronger than that. We don't have any ions here. So we need to determine if the molecule is polar or nonpolar. If it is polar, does it meet the conditions for hydrogen bonding? To do all of that, your first step should be drawing the Lewis structure. So I'll give you all some time to work on this. Let me know if you have questions. And if you finish, I believe the next slide is a learning check as well, so you can try that. We've got the Lewis structures on the board. Don't forget to consider geometry. We need that to also assess the overall polarity of the molecule. All right, we'll start going through these. What do y'all think for A, first molecule, strongest IMF? Go ahead. Was what? Oh, what is the strongest intermolecular force that each of these molecules would have if they were like a liquid, pure substance? What force would be between the molecules? So if you have a bunch of CH3OH, then what intermolecular force would be present? That's the question. So yeah. How do you know hydrogen bonding?
Because it attracts two polar molecules that are hydrogen.
Yeah, so it does. It attracts two polar molecules where we have hydrogens, and specifically the hydrogen is bonded to an oxygen, nitrogen, or fluorine. So in this molecule, we have a hydrogen bonded to an oxygen. This part of the molecule is polar and results in hydrogen bonding. I'll write it out. So if you had a pure sample, this is methanol. If you have a pure sample of methanol, that would have hydrogen bonding interactions between the molecules. How about difluorine, part B? What do you think? It's nonpolar, so what is the strongest intermolecular force between difluorine? Dispersion, yes. How about part C? What do y'all think? Is this polar or nonpolar? Polar? Why polar? Need to phone a friend? Yeah, you can.
Do you know, like, to draw that way, so, like, it is.
Yeah, good question. I had the same question earlier. Some of you may have drawn something like this, which makes it look like it's nonpolar, but this is why I said to think about geometry. So you think about the actual shape of this molecule. This is a tetrahedral molecule. I wish I had my model kit, but I don't. In a tetrahedral shape, you have 4 bonds pointing to 4 different corners of a tetrahedron. So 2 bonds are never 180 degrees apart, so their polarity cannot cancel out. The only time that a tetrahedral molecule is nonpolar is if all 4 of these atoms are the same, or if the actual bonds are not polar. So if you have two fluorines and 2 hydrogens, the carbon to fluorine bonds are polar. And that results in an overall molecular polarity where towards the fluorine area we have partial negative, and towards the hydrogen area we have a partial positive. In our notes, chapter 11.1 is molecular shapes, and 11.2 is polar molecules. There's a reason that's directly after molecular shapes, because we do have to consider the geometry of a molecule to properly assess its polarity. So with this molecule being polar, what's the strongest IMF here? What do you think? It's okay if you're wrong. I just need an idea. Thank you.
Would it be dipole, dipole?
Okay, so would it be dipole, dipole? What made you select dipole, dipole?
Well, I don't think there's a hydrogen bond because there's no H to O and F.
You got it. Yeah. So we have a polar molecule, so it's more stronger than dispersion. We have at least dipole, dipole. And then we check to see if we meet criteria for hydrogen bonding. We do have hydrogens present, but they're bonded to a carbon. So that does not meet criteria for hydrogen bonding. So the strongest intermolecular force here is dipole, dipole. And how about BCl3? Is this polar or non-polar molecule? What do you say? It's non-polar. How do you know it's non-polar?
Because the forces on each side are equal.
Yeah, the forces on each side are equal. I could see where you're pointing with your pen. The forces, the dipole from boron to chlorine, these are polar bonds, but they're pulling equally in all directions, so overall the molecule is nonpolar. So then if it's nonpolar, intermolecular force, dispersion. Thank you. All right. Questions? Feeling good? All right, we'll go to the next one. So this is all about dispersion forces only. We have diatomic gases, H2, N2, O2, F2, and Cl2. And the question is, which of these have the strongest dispersion forces and which has the weakest? When we're comparing these diatomics, what feature do we think about to answer this question?
Size.
Yeah, it's the size. Is that what you were going to say? Okay. So yes, we think about the size. So this is related to polarizability based on the size of these atoms. Remember, a larger atom, there are more electrons that can be polarized to create a dipole. So with that in mind, which of these have the strongest dispersion forces? Is it ECl2? What do you all think? Yeah? Or D, F2? Well, we need to consult patterns for atomic size. And all of hydrogen is in the first row. These three are in the second row. Remember, if you think about or look up a periodic table, they're all on the top right corner in the P block. Those nitrogen, oxygen, fluorine. Going left to right, atoms actually get smaller. So chlorine is smaller than oxygen, smaller than nitrogen. But as you go down a period, chlorine is right below fluorine. The size increases.
Can we use the electronegativity thing we know for determining like the strongest dispersion?
So yeah, so I don't know if everyone heard. The question is if you can use electronegativity. Are you thinking about the electronegativity trends?
Yeah.
Yeah, so the trend for electronegativity is the same for atomic size.
So it'd be D.
So it is. Oh, sorry. No. It's a different trend. Never mind. Different pattern. Sorry about that. It's not the same. Going down a column, we would decrease in electronegativity, but we increase in atomic size. So it is a different trend. I apologize. So the largest atom the largest molecule is Cl2 because that's in the third period and the rest are in the first or second. So this is the largest molecule, so strongest dispersion forces.
Can you draw the arrows if you do?
Yeah. So this would be increasing atomic size. And this way is so it's exactly the opposite trend for electronegativity. So the largest atoms are at the bottom left corner.
So for these trends, like going down the column takes priority over going on top.
Yeah,
right?
it does. Yes, what do you think is the weakest? You think fluorine. Okay, what makes you think fluorine? Yeah, so fluorine, yes, fluorine's all the way to the right. It's in the second row. It's smaller than oxygen and nitrogen, but hydrogen is in one row above it. Fluorine's in the second row, hydrogen's in the first row, up in the left corner. So you can't really see that H, but top left corner, it's in the first row, so that would be smaller than fluorine.
So fluorine is like stronger than oxygen.
What do you mean by stronger?
I guess stronger is good. It has more electrons.
It has more electrons, but it's a smaller element. It's a smaller atom. It holds its electrons closer.
You're like, we only use like the number of electrons when it's like grouping, like thinking or something. Like when it's like something.
Yeah, I see. Yeah. Okay, so weakest would be hydrogen because this is smallest. Remember, hydrogen only has 1 s electrons. Fluorine has 1 s, 2 s, and 2 p. Questions? Yeah, go ahead. Yeah, that would be smaller than, yes, than hydrogen. Okay, we're going to take what we learned about intermolecular forces and talk about properties of liquids. So properties that result from having stronger or weaker intermolecular forces. The first is viscosity. So viscosity is defined as a substance's resistance to flow. So I have syrup and a picture of syrup getting poured on a spoon and water getting poured on a spoon. If you think about pouring syrup, it pours out kind of slowly. You can see the syrup moving slowly towards the opening of the container, and it would pour and fill that spoon slower than water would. So syrup, the molecules in syrup have stronger intermolecular forces than water, so it has a higher velocity, higher viscosity. Syrup, one of the main ingredients in syrup is sugar or glucose. In the structure of glucose in a cyclic form, let's see if I remember from earlier. We have 6-membered ring. You can write this down, but I won't be asking you to reproduce this. 6-membered ring with carbons. Each carbon's bonded to an OH group. And then one is bonded to a CH2OH. And then there are hydrogens as well. Okay, so there are 1, 2, 3, 4, 5 locations where hydrogen bonding can occur in one glucose molecule. So there are strong intermolecular forces between the molecules that are in syrup, and that results in higher viscosity or more resistance to flow. Water is just H2O, and there's only 2 hydrogens and an oxygen. We can also apply what we learned about dispersion forces. This is a larger molecule, so it would have more stronger intermolecular forces than a smaller molecule. Very similar to viscosity is surface tension. So this is the tendency of liquids to minimize their surface area. And if a substance has stronger intermolecular forces, it has a higher surface tension. So you think about liquid sample, a bunch of molecules are present in the sample. A molecule not at the surface, so anywhere else, is interacting with all of the molecules surrounding it. So it has equal forces pulling in opposite directions. These are intermolecular forces. A molecule at the surface has interactions, attractive forces between the molecules next to it and below it, but nothing on top. So that pulls the surface molecules down into the liquid. So that is what surface tension is. If those interactions are stronger, then there's a stronger force of attraction between surface molecules, so a higher surface tension. Then we have adhesion and cohesion. So adhesion is the attraction of atoms and molecules to different particles. The root of the word adhesion is just like adhesive. They're sticking to different molecules. It's not really a stick, but they're attracted to different molecules. So water in a glass tube. Water molecules are attracted to the glass material. And so on the edges of the tube, water molecules are interacting. This is the glass material here. These are water molecules. They're interacting with that glass material, and that's why we get the meniscus, that lower part of the center of the water level. So if you had a beaker with water and you put a glass tube in it, the water would travel up the glass tube some amount. That traveling is called capillary action. So let's define that down here. I'm actually going to define it at the top. This is the ability of a liquid to flow against gravity up a narrow tube or a capillary tube. I'm going to draw an arrow to show we're describing this for water. So that's capillary action. Cohesion, so on the right side now, is the attraction of atoms and molecules to like particles. So if you have a beaker with liquid mercury in it, you put a glass tube in it, well, mercury is not attracted, doesn't have an intermolecular force between itself and the glass tube. So it's not going to travel as far up, and it's not going to interact with the surface of the glass, and we see an opposite shape here. The mercury is not interacting with the glass, it's interacting with itself. All right, let's do a learning check here. Oh, did you all have that typed out on your slide?
Yeah.
Wow. Well, that's okay. Okay, so in this learning check, we have 3 molecules. We have methanol, which we've already talked about in the previous learning check. We have, this is pentane, and then CH2Cl2. We're arranging these on this continuum from low viscosity to high viscosity. Once you arrange them, add another arrow that starts at the molecule with low surface tension and goes to high surface tension. I'll give you all a few minutes to get started on this. the first molecule here, what's the strongest intermolecular force? Do you remember from the previous learning check? Or just by looking at the structure? Yeah. It is hydrogen bonding. We have that OH bond. So this molecule has hydrogen bonding interactions. Remember pentane, just carbons and hydrogens. This is a completely nonpolar molecule. Thank you. Dispersion forces. And then CH2Cl2 is pretty similar to CH2F2, where we have two chlorines bonded to that center in a tetrahedral shape. And this one's dipole-dipole, yes. So that's the first step, is identifying the strongest intermolecular force between each of these molecules, assuming you have a pure substance of each one. So now that you know the intermolecular forces, then your task is to relate that to viscosity. So which would have low viscosity, which would have high. I'll give you all some more time to work on this. Let's start with high viscosity. When you think high viscosity, think syrup. Think something that flows really slowly. High viscosity, the molecules within the liquid have a strong attraction to each other. So a higher viscosity results from stronger intermolecular forces. So on this continuum, CH3OH would have the higher viscosity because it has stronger intermolecular forces. Then low viscosity would be weaker intermolecular forces. So that's our molecule with dispersion forces. And then dipole-dipole for CH2Cl2 is somewhere in between. Molecules with high or strong intermolecular forces also have higher surface tension. So on the right side, we have high viscosity and, well, I'll say stronger surface tension. And on the left, we have low viscosity and weaker surface tension. Yeah.
I was a little bit confused, so I thought pentane had a bigger molecule arrangement, so I thought that was a stronger ion.
Yeah, that's a good question. So you have the right two, or one trend is right, that a larger molecule has stronger intermolecular forces. When we were talking about pentane, we were talking about that nonpolar molecule compared to another nonpolar molecule that was smaller. So if we have two nonpolar molecules, they both have dispersion forces, but the larger one will have stronger dispersion forces. But hydrogen bonding is still stronger than dispersion forces. Yeah. Other questions? Okay. We'll start this next section. So we're now going to relate intermolecular forces to the energy required for something to go from a liquid to a gas, or liquid to solid, or solid to gas, or solid to liquid, just changing phases. So I have 3 pictures here, 3 particle pictures. These are all for water. Oops. For a second, look at these pictures and identify which is the solid, which is the liquid, which is the gas. Okay, which is on top, the top one here? Gas. Yeah, these particles are far apart. This is a higher energy phase for a substance, is the gas phase. They're moving around a lot faster, so they have higher energy. How about this one, bottom right? Solid or liquid? I had both responses in my earlier section as well. So this is a unique feature. Normally you would think particles closer together, that's a solid. But for water, their particles can get closer together in the liquid phase than in the solid phase. This is why ice floats on top of water, because solid water, ice is less dense than liquid water. When water gets into a solid, it has to kind of lock into the shape and see there's space between particles. When it's a liquid, it can get real nice and still. So other substances don't have that difference in density. Usually solids are more dense than liquids. But for water, it's slightly different. Okay, so this is the solid, and this is the liquid. And then each of the arrows on this diagram represent a phase change. So we'll start at the bottom. This bottom arrow, we're starting at a liquid, we're going to a solid that has the very technical term of freezing. So that's what that process is called, just as you would expect. Liquid to solid is freezing, and the opposite is melting. But in chemistry, we also call this fusion, and we'll use that term fusion to describe the process of going from solid to liquid. Now we'll work our way up. So liquid to gas, that is vaporization. So we have a liquid substance and it's going to become a vapor. So vaporization. The opposite of that, a gas becoming a liquid, is condensation. When you get condensation on the outside of your windows in the winter, it's in the winter or the summer, it's gas particles condensing on the window as they cool down. Solid to gas is sublimation. And then gas to solid is deposition. All right, well, oh yeah, go ahead. So it actually doesn't. There are processes to go straight from gas to solid, or solid to gas, like dry ice. You have solid CO2 and it will become a gas. Yeah, so it is possible to do that. But usually it would go to a liquid and then to a solid. All right, thanks everybody. Have a good weekend. I'll see you on Monday. Thank you.